Welcome, welcome. This is lecture 4 of Machine Learning and Bayesian Inference. In the last lecture, I tried to put supervised machine learning into a probabilistic context. And the underlying idea was just to say, okay, let's say that we model the data that we see and the stuff that we want to classify by having a joint distribution on the feature vectors and the class. Then just assuming that all the data we see, all the labeled data we see, is obtained by sampling IID from that joint distribution. And having set up that idea, I looked at how you can then think in terms of there being a parameterized collection of functions that describes the underlying relationship between feature vectors and classes, and then also have essentially a noise model that quantifies the uncertainty that you have in how labels for specific feature vectors are generated. And having set that up, I showed that you can get the maximum likelihood and maximum a posteriori methods for deriving learning algorithms, or more specifically for deriving errors that should be minimized in order to choose a weight vector to pick out some specific function from your underlying collection. And the way to think about that was, in the case of the maximum likelihood version, saying, if this is the model for my data, and I see some given data set, what's the most probable collection of weights that would have produced it? Or, for the maximum a posteriori version, flipping that around using Bayes' theorem and saying, what's the most probable collection of weights that I should choose, given that this is the data that I've seen? So there were two approaches here, which give you slightly different error functions, which just happen to be quite common ones that you see in the neural network literature an awful lot of the time. So that was a win, and we could uncover some assumptions that were involved. And having gone through that for regression using Gaussian noise on my examples, I then introduced a way that you can do it for two-class classification, and that's pretty much the point that I'd got to. So on this particular slide here, the really important expression was this guy, and that is saying that we still have some underlying parameterized class of functions with parameters w, but now we're quantifying uncertainty in the classes using this function here, which for now is the sigmoid. And that tells us the probability that x will be labelled as class 1 when we see it. And I finished off by just showing how you can use that idea to look at a model for the generation of linearly-ish separable data that has noise in its classifications. Now I've got a little bit of unfinished business still with this part of the lecture course, and then I'm going to put it to the side for a little while and do a little offshoot in a slightly different direction, because so far I've still been talking in terms of picking a specific collection of weights, which is what an awful lot of the machine learning literature and the current neural network literature does. But I want to make good on a promise of considering how one might solve these kinds of problems optimally, because the outcome of thinking about the optimal way of solving these problems gives us a slightly different outlook on what might be the best way of going about them. So that's where I'm going today. The first thing I need to do really is just to finish off what I'd left at the end of the last lecture. We have now this likelihood function that works with two-class classification. And that's just for a single example. But we can do the same trick as before now. We can say, if I've got some collection of training data, I can just say the likelihood is the product of the likelihoods for the individual examples under the IID assumption. So I can just write down the likelihood for a complete training set like this. but I'm doing a little bit of notational trickery here just to make it a little bit nicer. The likelihood for a single example can be written as in this equation here, because if you want to know the probability of a label given your feature vector and your weights, it's just going to be as defined when the label is 1, okay? Because we defined the likelihood as being the probability distribution for y, and of having this value if that random variable is 1. And that means that if the label is 0, the probability of seeing x labeled 0 for parameters y would just be 1 minus that likelihood expression. Okay, now that is two cases. It's not particularly nice to deal with, but here is why, for this particular part of the course, I choose the two labels to be 1 and 0 rather than 1 and minus 1. It's because that whole expression can alternatively be written this way, which makes it a lot nicer to deal with. Okay, and the reason that that works is because if y is 1, then I've got a power of 1 here and a power of 0 here, and I get just this part of the expression. And if y is 0, then I get a 0 here and a 1 here, and I just get this part of the expression. Okay, so that all works out quite nicely. And if we assume that the examples are IID, we can then just write down the likelihood for the full training set as the product of the likelihoods for individual examples. Okay, and then I can do exactly the same trick as I did a few slides back. If you just rewind a bit to the derivation for the regression case, you'll find that the posterior probability for the examples, the probability for the examples given W, has this format. Okay, that was derived earlier, and we can just plug in our new expression for the likelihood here. Now it's worth considering that just for a moment. I believe in the problem sheet, one of the problems is to now pull the same tricks as before and turn this into an error measure that you can minimize in order to train something by choosing weights. You should do those problems for the supervisions. But what you then have is an error function that you can minimize that looks different to the sum of squared errors, but is appropriate for two-class classification. And you can use that error function and plug it into the backpropagation algorithm if you like, or you can use it in whichever format you choose to use it in. Okay, it's just an error function that you can use and minimize to choose your weights, your weight vector W. But you should just note that it has still one particular similarity with the sum of the squared errors, which is that actually the sum of squared errors function still had this parameter denoting the noise variance in it. Okay, the uncertainty that we have attached to the noise in our data, and now we have theta, which is the steepness of the sigmoid function, which serves a very similar purpose. Okay, but the important point there is that something about the noise model that we use turns up in the error function that we end up trying to minimize. And again, from that expression, you can derive an error function which you can minimize, and it will give you the maximum a posteriori algorithm if you use this expression directly, or you can flip it around with Bayes' theorem, put a prior in on the weight vectors, and get yourself a maximum a posteriori algorithm. Sorry, did I say maximum likelihood algorithm the first time round? I meant with this guy at a maximum likelihood. I can't remember if I said the right one. Okay, I'm going to come back to that later in any case. It really is just exactly the same process as the derivation for regression. It's now been placed into a context that's appropriate for two-class classification. Now, so far, everything I've said in terms of supervised learning has involved a set of training examples that are labelled, and has involved picking some function to fit those by varying some parameters. And that's all good. Okay, it's how an awful lot of machine learning works. And I've also made reference to the fact that the aim here isn't just to learn to reproduce the training examples. It's to get generalization performance. And that means you want to end up picking a bunch of parameters which, when used on future data that you've never seen before, tends to classify them correctly. But what I haven't said is anything about how you might quantify that and how you might talk sensibly and formally about generalization performance. Okay? Because this is the really important thing. So far, although you've seen learning algorithms, you've seen backpropagation, and you've seen a more general way of deriving maximum likelihood and maximum a posteriori, I've only talked about choosing parameter vectors. I haven't talked about how you might have any confidence that in future use they're going to be any good for predicting new things. Okay, so standard running example, medical diagnosis. You train these things on some labelled data, on some actual patient data, then you get your classifier. Now what's actually important to you is that when you apply this classifier to new patients, it diagnoses them correctly a lot of the time. Okay, but how do we quantify this? Now that's quite important. We actually need a definition, and if we can get a definition for what good generalization is, then we can at least ask the question, what method is going to give us the best performance using that definition of generalization? And that's what I want to talk about now. This is an old classical method for talking about how you might address classification problems of the kind that we're interested in an optimal way in terms of getting generalization. We're going to start by making the problem a little bit more general, but a bit more general in quite an important way. Let's say we still have feature vectors or attribute vectors, which we'll label as x, and we still have a set of k classes. But now we're going to be slightly more general in the sense that we also have a collection of actions. Now those actions might just be that the first action says put this vector into class 1, and the second action says put this vector into class 2, and so on. But it doesn't have to be that way. Okay? The standard example of why it doesn't have to be that way would be that you might want to say, well, I decline to classify this thing. And I'll come back in a second to why that might be important. But the second way in which we can generalize this is to say we now have a measure of loss. The loss for taking some action when there's a particular class. Okay? So the loss, lambda ij, is a number that's associated with taking action I when the class is in fact class j. Okay, so hopefully that's clear. You see an x, there's a class associated with it, you take an action, and there is some level of loss associated with the action and the class. What then? Well, before I go further, let me just give you a reason why you might actually want to make things more complicated like this. Quite often, machine learning problems have an asymmetric loss, and it's a fairly natural kind of asymmetric loss. Once again, the standard example is medical diagnosis. If you are trying to diagnose a particular form of cancer, and a patient who is healthy comes to you and you say, you're healthy, we can probably safely say that your loss is 0. You got the answer right. If they have this form of cancer and you say you have this form of cancer, well, it seems reasonable that your loss is still 0. You got the answer right. The asymmetry comes if you get the answer wrong. And the reason for that is that if you have a healthy patient and you misdiagnose them as being ill, okay, it causes them distress, but it's probably not going to be life-threatening. You will assign some loss to this mistake. But that's probably a lower loss than if someone comes to you and they are ill, but you classify them as being well, because that can be life-threatening. Okay, their cancer goes undiagnosed. This can be very bad. And to make an error in that way, it seems reasonable that you assign a much higher loss to that possibility. Okay, so this is a somewhat more general framework. And sure, learning algorithms in general can be set up in order to have asymmetric loss and to take asymmetric loss into account. This is just the first step in looking at how you might sensibly do that. Now, having the extra action can also be useful here. In that particular application, it may be that if your machine learning algorithm isn't particularly certain about which way the diagnosis should go, it may want to defer to a human. They may want to be a class that says, "Don't ask me, buddy, I'm just a computer." And at that point, you bring in the consultant to help out. Okay, so this is, in some senses, an more abstract, more general framework, but it's actually trying to address real issues in the applications of supervised learning. But anyway, let's get back on track to where we are. We want to talk about generalization. Now, we're going to keep actually using a probabilistic model of the world in exactly the same way as I have been for the last couple of lectures. Okay, we're going to see feature vectors and classes that are generated according to some joint distribution. Okay, once again, we have this probability distribution jointly on the feature vectors and the class. This time we're going to split it in a slightly different way. Okay, if you go back a few slides, we've been talking about splitting it this way, and now we're going to split it this way. Okay, this just comes about because if you've got a joint distribution, you can split it into a conditional distribution and a prior in two different ways. Okay, that's just basic probability theory. It just serves our purposes at this point to choose one rather than the other. And the final two equations here, okay, these are just, once again, bog standard use of Bayes' theorem if you want to switch between one and the other. So one or the other. Okay, but we're interested in this guy here. Now, what are we going to do? Okay. Let's say we start looking at the occurrence of these feature vectors. Okay, these feature vectors from our data, whatever it is, come along. And every time we see a specific feature vector, we decide to take one of our available actions. Okay? There's a joint distribution on the feature vector and the class. Every time we see a specific vector, we take one of the actions. Okay? Sometimes when we see that feature vector, it will have one class. Sometimes it may have another. It may predominantly appear with just one of the classes and just occasionally appear with one of the other ones. But there's uncertainty here, which is why there's a probability distribution. Okay? That means if we take the same action every time we see that feature vector, then each time we'll make a different loss, because it will depend on which class we've obtained from that probability distribution. If we look at the expected loss that we get, then we have this expression. This is called the conditional risk. Okay? What it says is it's the expected value when the classes are being generated according to the probability of the class given our specific feature vector, and it's the expected value, it's the conditional expected value of the loss given that vector. And this is just the standard expression for the conditional expected value, in this case of the loss, under the posterior distribution of the class given this specific vector that we've chosen. Okay, everything here is for one particular vector. Okay, we're conditioning on a particular vector x. Okay? It's just every time we see it, we do the same action, and we do this many times. We're interested in the expected loss that we make. We can now take that a step further. Okay. Now, instead of having just a single specified feature vector, we say, well, what we actually want is a decision rule. Okay, a decision rule here is the equivalent of our classifier after training. Okay, it's the rule that we're going to use to classify new things. So it takes any feature vector and assigns it to an action. Okay, so this will tell us what action to use for any x that turns up. Now, if we want the overall expected loss that we make, this is called the risk, we have this expression here. Okay, we're taking the expected value for the joint distribution of the feature vectors in the classes, and this is the loss for the class we see and for the x that the decision rule tells us to take. Okay, I haven't specified the decision rule yet. We can do that in a minute. That's the whole point of the exercise. We want the decision rule that gives us the minimum possible risk. Okay, the minimum possible expected loss when we use it. This line just splits that expected value, okay, using this expression here, which is derived in the supplementary notes on probability. Okay, you can split an expected value on a joint distribution just as you can split the joint distribution itself. This is not controversial. Okay. But the point now is that this is the conditional risk from the previous slide. Okay, for the action that the decision rule tells us to take for a specific x. Okay, so we end up with this because we're dealing with feature vectors, so this expected value here is going to be an integral rather than a sum. So it's worth summing up what that's saying. Okay, what we're saying now is we have a joint distribution, feature vectors and classes. Okay. Pairs from that come along. Yeah, we can think in terms of just sampling this IID many times. Each time we see an x, our decision rule tells us an action to take. That x will have been paired with a class, so we'll make a loss for the action in the class depending on what the decision rule tells us. And if we keep doing this, this tells us the expected loss that we end up making, okay, as these examples come along. Now, what we want to do is minimize our expected loss. Okay? Minimizing the expected loss gives us the Bayes decision rule. And hopefully, if you look at this this expression here, you can see, and I won't prove this formally, but if you give it just a little thought, it should be pretty clear that the way that you minimize this in order to get the Bayes decision rule, okay, how do you choose the decision rule D in order to do that? Well, you just minimize the conditional risk for each individual x. Okay, you choose D of x to minimize that value for each individual x, and by doing that you minimize the value of this integral. Okay. Okay, so that's the kind of conclusion, although it may not seem just yet how we can make much use of it. Okay, but this is what you have here on this slide is the important sort of conclusion so far. If you've got some particular vector features, your Bayes optimal decision rule should take the action that minimizes the conditional risk. Okay, and if you do things that way, you minimize the expected risk over time. Okay. Now we have to take that and do something useful with it. Okay, so we'll come back to this slide in a moment, But now we have to ask the question, well, how do we put this into a context where we can actually get something meaningful for the purposes of doing supervised learning? Let's try a simple definition for what generalization means. Okay? Let's say that in supervised learning our aim is often to work in such a way that we minimize the probability of making an error. When predicting a label for a previously unseen example. Hopefully that sounds sensible. Okay? We train our system using some label patient data to do diagnosis for some condition. Okay? We then try it out. We show it some new patients. Let's say that it generalizes well if there's only a small probability that it makes an error. Okay? Hopefully that sounds like a good definition of generalization. In fact, if you actually look at the wider work in computer science on analyzing generalization performance, it is the definition of generalization that you will see almost all of the time. Okay? Good generalization means there's only a small probability of error when you classify previously unseen stuff. Now, the key point here is that we can define loss in such a way that minimizing the expected loss would correspond to minimizing the probability of error. And this is quite straightforward because we have, again, quite a straightforward little result in probability theory, which is proved in the supplementary notes. It is that if we take the indicator function of an event, so we have a function that is 1 when a particular thing happens and 0 when it doesn't, and we take the expected value of that function, then we get the probability of the event. Okay? Think of this a slightly different way, alright? Probability is nice when you think about flipping coins. Let's say I have a biased coin. My event is that the coin comes up heads. Right? Let's think of the indicator function for that event. Every time I get a head, I count a 1. Every time I get a tail, I count a 0. Okay? If the coin is unbiased, about half the time I'm going to get a 1. And the expected value of that indicator function, the expected value of these 1s and 0s, is going to be about a half. Similarly, if it's very unlikely that I get a head, and I sample this coin many, many times, I'll get relatively few 1s and quite a lot of 0s. The expected value of that indicator function, okay, the average of the 1s and 0s is going to be small. Small probability of a head. Okay, we're talking about exactly the same thing here. This just lets us write it down formally. So, what that says essentially is that if I make the loss 1 for an error and 0 when I get something right, and I look at the expected loss, I end up measuring the probability of error. You might want to wind that back and listen to what I just said again, okay, because it sums it up in a nutshell. Let's make it a little bit more formal and explicit. If I've got k classes, it's a k-class classification problem, and I have the same number of actions. Okay, action 1 says put this vector in class 1, action 2 says put this vector in class 2, and so on. And we define the loss, here's the important bit, as being 1 if I put the example in the wrong class and 0 otherwise. Then the risk looks like what we have in this this box at the bottom of the slide. Okay, the conditional risk in this case is the expected value of that loss, which is just the probability the decision rule chooses the wrong class. And the Bayes decision rule wants to minimize that for all possible vectors. Okay, for all possible feature vectors. So the key conclusion here is that if we make a loss of 1 for making an error and 0 for getting our class prediction correct, then by minimizing the expected loss, we maximize the probability of getting the right class, okay? Or by minimizing the expected loss, we minimize the probability of making an error, okay? And that's what we want in order to get generalization. So the only thing that's left is to say, well, how do we choose the decision rule in order to get that minimized risk? We've just seen that in order to minimize the overall risk, we minimize the conditional risk individually for each feature vector. So here's the conditional risk for a given feature vector x. This is taken directly from a derivation a few slides back. What we're saying here is let's always choose action I, meaning we'll put x in class I. Okay. What is the expected loss if we do that? Well, every time one of the other classes comes up, okay, every time I is not equal to j, we make a loss of 1. So one way we can think of it is that we get this expression here. But alternatively, because I is the only other possibility, the expected risk in this case must be 1 minus the probability of seeing class I, which is the one we're predicting, because we're always choosing action I. Okay, so if we always take action I saying we think x is in class I, when we see this specific x, the conditional risk is 1 minus the probability of that class. And we want to minimize this, so we want to maximize the probability of class I given x. So we should choose the action for which that probability is the greatest. Okay, and that's the big conclusion here, which sounds perfectly reasonable, I hope. Okay, the decision rule should choose the class for x that maximizes the probability for the class given x. Okay, and if we do that, we end up with a decision rule that minimizes the probability of making an error. Okay, that's the big conclusion here. Okay, but I don't think I can really emphasize it enough. It's minimizing the probability of making an error when we have unseen data. Okay, that maybe wasn't used in designing our decision rule. Okay, that's what we're aiming for. Now, given that that's what we're aiming for, we should probably just remind ourselves of how the overall thing is going to work. I've just talked about a decision rule that minimizes the probability that you make an error when you use it. But we want to choose that decision rule on the basis of some training sequence. Okay, so we should probably talk in terms of something that depends on a training sequence. We've also been talking in terms of having some kind of model of how this data is generated. And usually in terms of some kind of parameterized model, so that by choosing the parameters in some weight vector w, we get our underlying function h that describes the relationship between feature vectors and class. Okay, and we've had a noise model introduced, and these things probably ought to appear in our formulation of this Bayes optimal classifier as it applies to supervised learning. Well, if you carry through the derivation of conditional risk and just let it depend on the new x that you're trying to classify and the training set that you've seen, you'll find that you get basically the same conclusion, and that you want to maximize this probability. Okay, you want to choose a class that maxes the probability of the class conditional on the thing you're trying to actually assign a new class to and the training examples that you've seen. Okay, that's step one. We need to put back in the idea of this underlying relationship between the feature vectors and the classes. How do we do that? Well, if we want to maximize this guy. We can use a little trick of using marginalization backwards. Okay, now I think this is mentioned again in the supplementary probability notes. Usually when you do marginalization, you're trying to get rid of something. But you can also use marginalization to reintroduce by going backwards. Okay, and that's what we've done here. We're interested in maximizing this quantity, but we also have an underlying model. But of course we don't know what the correct H is, because we're trying to choose something on the basis of training data. But we can put H back into the equation like this. Now, I'm summing over all possible relationships here, okay? If it's parameterized, then you're choosing a weight vector that then tells you what H is, and this sum becomes an integral. Okay, and that's how I'll write it a bit later. But I think sums are maybe easier to think about. So let's just say we have a finite number of possibilities for what H could be, and we're trying to construct a Bayes optimal classifier using those. What I've done to get to the second line is the usual trick of splitting this joint distribution here into two distributions. Okay, this is the usual thing. Probability of A and B is the probability of A given B times the probability of B. And we can just keep the conditioning events on the right-hand side. And then to get to the last line, I've made the assumption that the probability of having some underlying relationship H, if you know some actual labelled examples, and then just have a new thing that you want to classify, is independent of this new thing, because you haven't seen the label on it. Okay, so it's not really telling you anything about H. And here, I'm assuming that the probability of a class, given the underlying relationship and the thing you're trying to classify, is then independent of the training set. Okay, because H is telling you about the relationship between X and C, and the training set isn't really helping you then. So these are assumptions about independence, and we end up with this relationship. Now this is telling us something very important indeed. Okay? What this is saying is that we've been thinking all along in terms of a model of how the data is generated, and we've been wanting to find a way of classifying new data by basing everything on that probabilistic model of how the data is generated. And that data generation model has the relationships H and the noise model, which turns up in the likelihood, okay, because this is the likelihood that we saw before. And we've now seen that the Bayes optimal approach to this tells us that we should maximize the probability of the classification given our training set S and the new thing X that we're trying to find a class for. And what this tells us is that we don't just use one of the H's. Okay? Everything up to now has involved picking one of the H's, either directly or by specifying it through some weight vector or other. What this is saying is that you sum over all possible H's, but you weight their predictions according to how probable they are, given the data that you've seen. Okay? The posterior distribution here says, what's the probability of seeing some particular H given the data? Okay. For each of those H's, we actually use the likelihood to make a prediction for what the class is, but we weight those predictions by the posterior probability. Okay, so we take the average prediction over all the possible H's, weighted by how probable they are. And this is telling us that that's actually what we should be doing if we want to do this optimally and minimize the probability that our decision rule makes errors. Okay, that's worth thinking about for a bit. Okay, I'm going to summarize it once again. Okay, our classification, if we're picking h's without parameterizing them, and we can write this as a sum, looks like that. If we're doing what we would usually do with neural networks or linear regression or whatever, then we're choosing weight vectors, and these are real valued weight vectors, so the sum becomes an integral, and we get this expression here, which is the equivalent. Now, in this case, instead of the posterior distribution of some particular h given s, we now have the posterior distribution of some weight vector given s. Well, we've seen that before. Okay, we were maximizing that in order to choose w for the maximum a posteriori algorithm. Okay, we were just picking a specific w that maximized it. That's the map algorithm. What we now know is that we should be using that as a weighting. We should be going over all the possible weight vectors w. We should use the likelihood here to work out what we think the class should be given that particular w, and then we should be averaging over all of those predictions, weighting by the posterior distribution here, probability of w given s. Okay, so we're not choosing a single relationship h or h sub w, depending on the circumstances, between the feature vectors and the class. We're averaging over all possibilities, weighted according to how certain we are of having got the right one. Okay, now, that is important. This is the essence of the Bayesian approach to supervised learning. And I'm going to come back to it a little bit later, but I think it's worth actually introducing it now, because it may take you a few attempts at just thinking this last bit of material through in order to see exactly what's going on, because I admit there's quite a lot going on in this lecture. The last thing I will say is beware. That's the optimal classifier, so it's tempting to then say, well, that's just what we should use and have done with it. Well, in a sense, okay, yes, it's the optimal classifier. If you're interested in 0-1 loss, and your appropriate definition for generalization is that you want to minimize the probability of making an error. Even if this is correct, it might not always be, but even if it is the case, this calculation, okay, the one from the last couple of slides that I've just been deriving, is often intractable in even the simplest cases. Actually working out this expected value, either by evaluating the integral or the sum, depending on which scenario you're in, it's generally something that you can't do. Okay? So, I will, at various points in this course, be introducing my commandments of machine learning. This is the first one. Thou shalt beware of Bayesians bearing gifts. What has happened here is we have derived the optimal way for doing supervised learning. And then I'm afraid I've rained on the parade by saying you generally can't actually compute this integral. You generally can't do it this way. Now, where does that leave you? Well, it leaves you with two things. The first is that, as we shall see a bit later on, one of the payoffs of computing things using that integral, or that sum, is that it gives you a systematic way of getting a measurement of how certain you are about a particular prediction. This can be important, but you can't do the integral, so where are you? Well, you have essentially two approaches. You can approximate the integral by trying to solve a slightly different integral, one that you can solve but which you hope gives you an answer that is close to the correct one, or you can use something called Monte Carlo Markov chain methods to approximate the integral, and you'll get a better approximation depending on how long you're essentially willing to wait. So you can get important payoffs from this approach, but you can't necessarily do it analytically, and we're going to have to talk a little bit later about some of the methods that you can use to try and actually get a good approximation to this full Bayesian solution. The other part of the story is that if you don't need the full-blown apparatus, and you don't necessarily need to quantify the uncertainty in your predictions, non-Bayesian methods can still be extremely good. And an awful lot of the methods that are popular at the moment are non-Bayesian because they don't quantify the uncertainty in your predictions. Okay, and for that reason, this course still talks about things like support vector machines and linear regression and various other approaches to solving supervised learning tasks. Okay, but the key message for today is that the optimal way of doing supervised learning involves computing these expressions, not just selecting a single hypothesis or a single weight vector, but averaging over all of them and all the predictions they make, weighting according to how probable they are in the light of the data that you've seen.